cholesteric liquid crystals, but to get there, I would like to yes, I would like to talk about cholesteric liquid crystals, but to get there, I would like to talk a little about chirality. So, chirality, as we know, represents broken inversion symmetry, and there are molecules of liquid crystals which may themselves be chiral, and in many cases, chiral molecules are added to liquid crystals. And there are some interesting things that happen. In isotropic systems, chirality gives rise to rotation of the plane of polarization of light, and in other systems, in anisotropic materials, one can get photonic bandgap. So, one question to ask then, I guess, is how to describe what is epsilon in chiral materials. Obviously, this is key to describing light propagation in chiral media. So, let's think first about isotropic materials, and sugar water is a good solution. So sugar is chiral. You dissolve sugar in water, and you'll find that if you shine plane polarized light through a container of water with dissolved sugar, the plane of polarization will rotate. And so it's interesting to ask how this comes about. Yeah, let's leave this for a moment. So one example is Pasteur's famous experiment with tartaric acid. And as I said, there are many naturally occurring molecules which are chiral. So how to deal with this in optics, how to describe it. And so broken inversion symmetry gives rise to pseudo-scalars and possibly pseudo-vectors, and so in some sense that's what we are looking for. If you have a handed object, like my hand, you can make three orthogonal vectors, and from these three orthogonal vectors, A dot B cross C, we can make a scalar that has the property that if you invert your coordinate system, the scalar will change sign. So this is a pseudo-scalar. And so handed objects then typically have a structure that allows the existence of pseudo-scalars. So that's the kind of thing that we expect to see. But the question is, even if we can identify these bodies, what is the structure of epsilon? And there are different descriptions of the optics of chiral materials, but Agranovich has, I think, a very nice approach which basically relies on spatial dispersion. And so the idea is that if we say that D equals epsilon E, and we know that this has to be in Fourier space, so epsilon must be a function of k and omega. Now, everyone is sort of familiar with the omega aspect, but not so much with the k aspect. And so if the system is non-local in space, then we want to somehow end up with manifesting the k dependence of epsilon. Now we don't know really too much about the details of what happens, but the idea is that if epsilon really depends on k, then we can expand in powers of k, and so we would get, for example, epsilon being equal to some epsilon 1, which has no k dependence, and then another term which would have a k dependence. But now, so here we have to think, so this is, epsilon is a proper second rank tensor, so we have to make a term here which is a proper second rank tensor, and we have to have a k explicitly in it somehow. Okay? So we can make a term which is I want to make sure I get this right. Which is just some quantity that we don't know. I'll call it gamma. So we'll have an I here just for convenience. And then we have k cross. Right? So this is a second rank tensor. We can write it with Levi-Civita. Contracting on one index, we get a second rank tensor. And in order for this to be proper, because Levi-Civita is pseudo, this must be a pseudo-scalar. Right? So having a system where epsilon had this structure, then we would have d equal to epsilon 0 omega. This is just a number now, plus, no, sorry, this would have to be the identity now, and then I gamma k cross E. And it turns out that if you then substitute this into the wave equation and work it through, then you get optical rotation. And you find that theta, the optical rotation, is equal to 1/2 gamma times 2 pi over lambda naught squared times z. So if you have a container of, let's say, an aquarium full of sugar water, and you shine light polarized this way, it will go through here, and when it comes out on this side, the polarization will have shifted, will have rotated by theta as light is going forward. So this is a nice way of describing what happens, and it takes into account generally non-local response of materials. So materials which have spatial variation essentially on the length scale of the wavelength of light. If it's much longer than that, then we don't see it. So this is optical rotation. It's a nice experiment to do, and it's fairly straightforward. And this gamma is a length. And as I said, it's a pseudo-scalar which changes sign if you change, if you invert your coordinate system. So this is just a way of describing light propagation in chiral materials. So this, I think, is a nice story. Then Another perspective which is equivalent to this is basically is just to note that I k cross E is equal to I omega B from Maxwell's equation. So if we have a k cross E appearing via our epsilon, then we can write that D is equal to some epsilon E plus we'll get some coefficient here times B. So there are scenarios where people don't talk about spatial dispersion, they just simply postulate that one can write the constitutive equations like this, and then B would be some other constant, maybe gamma is not the best one, times E, I'm sorry, this is H, plus some other constant times H. So another way to go is to somehow specify these coefficients here, but I think it's a much cleaner and physically more approachable picture to use the notion of spatial dispersion. But really the only thing that matters is how your polarization is distributed in space, which is where this term is really coming from. Well, that's pretty much what I just said. Just doing it in terms of indicial notation. And yeah, so one gets these two circularly polarized modes, right and left-handed, propagating at different speeds, and these two together are equivalent to plane polarized light rotating the polarization direction. So a nice question to ask is, where does this gamma come from? And we made a little model just for amusement. So imagine that you have an object which is basically just some kind of a solid, say a wooden piece here with three pieces of wire, which this one is in the plane of the screen. Here the tip comes out a little bit, here the tip goes in a little bit. So that's a chiral object. And then you can simply work out what the dipole moment is if you put this in a field. And you sort of grind through this, and then you find that you get indeed a term which is exactly like this term that I put on the board. And there's some interesting length scale issues that, you know, so when you think of a chiral object, you think of a helix, and the helix has a pitch. And so somehow you think that maybe the more chiral the object is, the shorter the pitch. But it's subtler than that. If you take two threaded rods, so two cylinders with threads on them, and suppose the threads are very fine, very closely spaced, and if you put them together, they tilt a little bit, but only a little bit. And it's only when you make the pitch much bigger that the tilt gets bigger when you push them against one another. You would think it would work the other way. You think that the tighter, the shorter the pitch of the threads, the more chiral the thing it is, the more turns you get per centimeter or something. But in some ways it works the other way. So yeah, here too, you see that this length, which sort of plays the role of the pitch, is in the denominator. Anyway, I just wanted to show you this. It's interesting to speculate. Now, people have talked for a long time about how to quantify chirality. And I don't think there is a way, of course, because it's a yes and no proposition. Is something chiral or not? To measure it depends on what metric you want to use. But certainly in optics, we can measure the effects of chirality, and we want to be able to relate the structure with the optical response of the bulk material consisting of many of these things. We were interested in trying to make a convex body which is chiral, and so we made a kind of a twisted ellipsoid. So it basically, it's an ellipsoid and you just twist it, and so we printed it, and it's pretty interesting in some ways. And the equation looks like this, and so you can see that there is indeed a sort of a pseudo-scalar lurking in here, which is not dissimilar to the quantity that I was showing you before. So it's just interesting to speculate how particle shape correlates with the dielectric tensor, which tells us about light propagation. Okay. There are many people who are proposing different metrics to measure chirality, and of course every metric gives a different result. Okay, so much for chiral materials. So as I said, there are these two schools of thought. One is basically by Landau Lifshitz and Agranovich. He's wrote a beautiful book just on spatial dispersion, and then Drud, Born, Fedorov, who do this real space description. But there are some interesting questions that remain, particularly involving boundary conditions. Yeah, in fact, there's some interesting questions in general about what happens on boundaries when you have chiral objects. Okay, so now I want to turn to helical cholesterics. So helical cholesterics, I'm sure everyone knows, are basically systems which are chiral, and we have rod-like molecules, and if I have boundary conditions, so the molecules all point towards the window, then in this chiral system, as I come up, the director will rotate and eventually trace out a helix, and we are interested in light propagation in these materials. Now, to make these materials, typically people take a chiral dopant, a pretty highly chiral molecule, and dissolve it in an ordinary nematic, and then you get this chiral structure. And so one noticeable feature is that these systems are periodic, and periodic systems have interesting properties, and that's what will be manifest in a minute. And here, what I want to stress is that we can't use Green's function because the system is not homogeneous, right? So it is as though you had a resistor and a capacitor varying in time. If you want to determine the temporal response, you can't use Green's functions. So we just have to forge ahead carefully. And so the idea is that the permittivity is a function of position, and we just need to try to ignore non-locality and work in real space. And so that's what I want to do, and it's fairly straightforward. And the really interesting thing here, in my opinion, is this very nice result from Floquet back in 1880, who said that if you have second order ODE with spatially varying, spatially periodic coefficients, then the solution will be of this form, e to the I mu z, and this is a periodic, phi is a periodic function of z. Then the allowed solutions are divided into bands where mu is real, and you just have some nice stable solutions, and bands where you don't have stable solutions. And it turns out that this has really, really important implications in electronics and optics both. But I don't have it here with me. But the point is that the Schrödinger equation that describes the behavior of electrons in solids is just like that. It's a second order ODE with periodic coefficients because the crystal lattice potential is periodic. And so that's why we have bands, we have valence band, conduction band, and all of electronics is based on that. Okay? And in optics, it's the same story. We have a periodic dielectric constant. We have bands, basically where light propagation is forbidden, and that's the photonic band gap that will become manifest in a minute, I hope. Right, okay, so I won't put everything on the board, but hopefully we can walk through this. So the basic structure then is this. We have molecules, but I really intend to describe the director orientation. So the director rotates in space, and when the director has rotated 2 pi, we've covered a distance, which is the pitch. So this is half a pitch. And we have basically ellipsoidal molecules with large polarizability in one direction, small in the perpendicular one. And it's convenient to construct a rotating frame which rotates along with the director. So this is a rotating frame where eta is always along the director, and phi is always orthogonal to the director. And so we have to solve typical usual wave equation. And but in this rotating frame, it turns out that the dielectric tensor is really, really simple. We just have these 2 scalar values in these 2 positions, and that's all that there is. And it's convenient to write the field as just two scalars indicating magnitude of the field component along the director and perpendicular to the director. Okay, and that's pretty much it. Then you put this into the wave equation that I just showed you, and we get these 2 coupled equations here. And so what I want to point out that Q is just the pitch of the structure. Q is just 2 pi over the pitch of the structure. So this is sort of the wave vector of the structure. And whoops, going backwards. K is the wave vector as usual. And now, so what do we have? We really know omega. It's our light source. We know the values of epsilon. So again, we know Q. So again, we know everything except the refractive index, which again plays a role of an eigenvalue here. So we can solve these 2 equations simultaneously and solve for n. Now n doesn't appear here explicitly, but n is just omega over k. Omega squared over k squared is n squared. So one then gets this simple equation for n squared, and this is the average epsilon, so just the average of the 2 elements, and this is the anisotropy, just the difference between the 2. And that's pretty much the whole story. So what we see then is that we have 2 values for n squared, and of course n can be positive or negative, indicating light propagation one way or the other. And so So if I draw a picture of n squared versus the pitch divided by the wavelength, then let me check this as well. No, I want it the other way. Lambda over the pitch, and I just plot these two branches, then I see two things. So when the pitch is infinite, then I just have an ordinary pneumatic. Then I will have two values here for n squared, which are going to be epsilon parallel and epsilon perp, as you would expect. And then we have these two branches, and this branch goes up, and nothing interesting happens, but this branch comes down, and it goes negative at 2 points. And so this is interesting, because when n squared is negative, then n is imaginary, and we have a solution which we have assumed to be of the form of e to the I n two pi n over lambda times r, let's call it z, the propagation direction, minus omega t. And so what we see then is when n squared is negative, this point becomes imaginary, and we have a real number up here, and we have exponential decay or exponential growth. So this then is the band, so this is the photonic band, where there are no stable solutions, exactly as Floquet's theorem said. I mean, it's even the same form, if you like. So, and all of this is coming from the periodicity. So here's a picture of what this looks like. So E is a function of position, as we said, because we are in a frame rotating along with the two vectors along the director and perpendicular. And so, but we have this range in between here where we can solve exactly where this guy goes to 0, and this ratio of lambda over p is equal to epsilon perpendicular and epsilon parallel here. So, and all in this whole region, there's no light propagation in the sample at all. So if I have a cholesteric sample, and the molecules, let's say, are here and they are rotating as I go through the sample, and I'm shining light along the axis. And now this is the point that this solution, although it's analytic, it only holds when one is moving along the helix axis. So K has to be along the helix axis. Off-axis solutions are just not tractable, unfortunately. So we find this really fascinating thing that we have this photonic band gap, which is simply produced by the periodicity of the crystal. And it has nothing to do with the chirality of the molecules per se, other than they are produced, that the periodic structure is produced by the chirality. So in a little more detail here, this slide shows what happens. So again, so we have two modes, one parallel to the director, that is not correct. We have two modes, each mode containing a part parallel to the director and a part perpendicular to the director. In the limit, when the pitch is infinite, we have an ordinary nematic, and we got the two modes we talked about earlier. The electric field is, so we have the extraordinary mode and the ordinary mode here in the nematic as before. But then as we move away along this branch, which is the solution with the positive sign when we looked at the equation for the refractive index, we get this solution, and nothing really interesting happens. This plane polarized light becomes more and more circularly polarized. And along this branch, though, things are interesting. So we have polarization perpendicular to the director, which then becomes elliptically polarized, almost circularly polarized, back to being perpendicular to the director. And then there's no propagation in here at all. And then at the other end, we come out parallel to the director and eventually become circularly polarized again. So one interesting thing is to think about what happens to the photons that are incident on the material in the band gap. So this exponential decay, the photons penetrate into the material, but they work their way back out. There's no power propagation into the material. If you sort of think of Maxwell's equations, because the wave vector ends up being imaginary, the magnetic field is out of phase with the electric field, so there's no net pointing vector energy flowing into there, no power flowing into the material. So photons go in and eventually they wander back out. And at the two band edges, we have standing waves, and I mean the n is 0 here, and this corresponds to standing waves polarized perpendicular to the director at one band edge and parallel to the director. And the further you go in away from the band edge, the more rapidly the photon number decreases as you go in. So, so this is the band gap, and it works pretty well, and there's lots of it works well in the sense that experiments agree very well with theory. The ordinary twisted nematic cell works on this idea as well. In a typical old-fashioned TN cell, the director rotated throughout the cell, and light followed the rotation, just like I indicated in these eigenmodes here. So these two modes follow the director rotation. Okay, they don't become depolarized. And if you applied a large field, molecules lined up along the field, then that didn't happen anymore, and cross polarizers would make the segment turn black. So this idea was used already a long time ago. And so that's where we are. So this is pretty much the picture of what happens inside the material. And then now we can talk a little about what might be potential applications. So these materials make good filters, although it's true that they only work for one-handed polarization. So, but just the same, you can get rid of half the light in one range of wavelengths, and if you want, you could split incoming light into two modes and make a filter for each of them and then combine them together again. to make it more efficient. So this is the sort of thing that you see. So this is a cholesteric film between pieces of glass, and we wrote this image of this nice dog in here with a laser. But this iridescent color is typical of what you see in cholesterics. And these are just scarab beetles illuminated with left and right-handed circularly polarized light. And so these wing covers are chiral, but these are not liquid crystals. They are solid chitin materials where the optic axis rotates throughout the sample. So what we did here, we just put a tunable wave plate in that changed the polarization from one side to the other, and just by changing the retardation, you can make the color change continuously from one to the other. Okay, so, well, this is what I mentioned before, that essentially Floquet's theorem constitutes underpinnings of electronics as well, and more recently photonics. So if you look at the reflectance of a sample, it would look something like this. If the sample is finite, if it is very thick, then it would be more like a perfect rectangle. And this is the more conventional picture of a band gap. But I think that this story here is rather elementary and also perhaps illuminating. Now, I want to say a few words about lasing, because to some extent, cholesterics are like cavities inside the material. To make a laser, typically people use two mirrors, and you have a standing wave between the mirrors. Photons bounce back and forth, and only certain wavelengths are permitted, and so you have light bouncing back and forth. Some leaks out through the mirror at the end, and you have to replenish that. So we have some phase condition here, and we have some loss, and we have some gain. So we have some absorption as we go, and we have to have some gain. And so this is typically done by putting a dye in the material and flashing a light on the dye, so the dye molecules are in an excited state, and a photon going by will cause a stimulated emission, and so you can make up for the photons that come out through the mirrors. So you go around, you have reflection, and you go back the other way, and you want to stay in phase in order to make sure that you have coherence and the modes don't add to zero. And so if you have satisfied the phase condition and you have made sure that you have enough gain to make up for losses, then you can get lasing. And basically that means that the phase, whoops, going the wrong way, that the cavity defines the allowed wavelengths, and you need a threshold to overcome losses, and this is your gain curve from the dye. And so if the gain curve is big enough, then you can get lasing at these various frequencies. There's another way to look at this, and Fermi liked to talk about the density of states, and the idea is that when you have excited state dye molecules, the probability of a photon being emitted is proportional to the number of states available for the photon to go into. So the density of states basically determined where in the spectrum you would have emission. And the density of states is very simple. It's just dk by d omega. And so if you have some bare emission rate of the dye, then it gets modified by this density of states. And And so the density of states then essentially looks the same as the wavelength condition we had before. We have again the bare emission rate for the dye, and then when we put these two things together, and if we have material which is above the threshold, then we get lasing here. So that's another way of looking at the lasing story. And now, if you look at cholesterics, if you look at this picture here, then you can see that we can calculate the density of states at the band edges, and they diverge nicely because we have this n in the denominator which goes to 0. So we have diverging density of states, so we can get these cholesterics to lase just by simply putting some dye in there, pumping the dye, and even though we don't have any mirrors anywhere, we get beautiful, beautiful laser emission at the band edges. So you just take a laser, little cholesteric sample with dye in it between pieces of glass, and you pump it with a dye laser, and you get this beautiful laser line right at the band edge where you would expect to get it. So that's a nice application of these materials. So you can have nice lasing. And then, of course, the question is, it would be nice to tune the photonic band gap. And so the question is, how can you do that? And so the cholesteric is kind of a given thing. You've made the mixture. It has a certain pitch. It has certain refractive indices that determine where the band gap is. And so to change that, it is not a simple matter. But one way to do that is to make the liquid crystal into a solid, make it into a rubber. And so Heino Finkelman made a very nice cholesteric liquid crystal elastomer. And now if you stretch this elastomer, then you're changing the pitch. And so you can change the laser line because essentially you're moving the band edge just by mechanical stretching. So one can tune the band gap mechanically in this way. One can also tune it by changing the temperature. So as I said, in the dielectric constant, we have the order parameter everywhere. And if you change the temperature, as you see on the slides of S versus T, you change the temperature, you change the order parameter, and you change the dielectric constant, you change the refractive index, and you can change the reflection band. Now, it's not particularly good because it's not very accurately controllable, and also the amplitude really changes a lot. So although that's one way to do it, it's not very good practically because it's, as I said, it's hard to control accurately, and it's also kind of slow. So the question then is, what are other ways to do this? And that's what I want to talk about next, is to make these heliconical materials where there's alternate ways of tuning the photonic band gap. So I think I'll stop here and leave some room for discussion. I wanted to go back to maybe 2 points, or maybe just 1 point. When we're talking about the Frank energy, we're talking about the elastic constants and how one needs to calculate those somehow from the intermolecular interactions. There's another interesting story there that plays into that picture, which is that if you have a gradient in your system, then you can have unexpected effects just due to symmetry considerations. So So suppose that you have suppose you have a director field which is spatially varying, then you can look at the divergence of this, and now you have a proper vector. And if you know that there's a vector there, the electrons will know that there is a vector there, and there will be electric polarization. This is called flexoelectric polarization. Okay, so simply by having a vector in your system, you will give rise to electric polarization, and that polarization will have associated energy with itself. It will polarize the neighborhood. So this will definitely make a contribution. And so this is something that is an interesting subject in itself, but when looking at calculating elastic constant, this is something that needs to be taken into consideration. The symmetry arguments turn out to be really powerful. There's another joke, let me finish with a joke, which is that in England, everything which is not forbidden is permitted. In Germany, everything which is not permitted is forbidden. In France, everything which is forbidden is permitted. Okay, so that's a joke. But the serious thing is that in a totalitarian system, everything which is permitted is compulsory. And physics is like that. So Murray Gell-Mann, I think, articulated this in one of his papers. So if something is allowed by symmetry, it must happen and it will happen. And this is just one instance of that. Okay, so if there's a vector there, then you can make another vector. And a really beautiful example of this is Dan Frankel, who is here, I guess. Everybody knows Dan Frankel, right? No? Yeah. So, so he had this idea that, well, suppose we take a hot object. So I just take some hot spherical particle and I put it into some environment. Then there will be a temperature gradient and there will be heat current, and there will be electric polarization for exactly this reason. So if you look at the divergence condition, okay, conserving energy, how the heat flow goes, then you'll see that this thing here, due to the electric polarization, this looks like an electric monopole. So the idea, again, essentially is the same as this. You have a vector here, which is the temperature gradient, so you will have electric polarization, and the thing is like an electric monopole. So it's a crazy idea, but then they did computer simulations, and it looks like this really happens. So it's just an interesting thing to think about what kinds of symmetry allowed terms can exist, and then you can make, I think, useful predictions based on that. All right, I'll stop here. Thank you.
Okay, we have time for questions. Let's see, let me start here. So, putting together your auditive talk, so I know that you have not directly talked about phase transitions. So do you know of any liquid crystals that would have good first order transitions as to be serve as energy materials?
Well, they certainly have first order transitions.
I mean, first order transitions, but that go to a ferroelectric phase.
No, not to a ferroelectric phase, no. But they can be used to some extent as heat pumps in the same way as other phase transitions can. And Mark Warner and I did something along these lines with liquid crystal elastomer, but not ferroelectric transitions, certainly. Yeah.
And the banana shapes types, they have some first order transition, right? So,
well, bananas are interesting because there you have really interesting behavior. Again, symmetry mandated, as it were. But I don't know. So, yeah. So they have polar phases, but I don't know how to. I don't know how one would control these.
so
Well, I mean, cholesterics, of course, have ferroelectric phases.
but it would be because there is one of the banana shapes. I don't need to remember that. It's that can go from the isotropic to polar phase.
Right.
To a ferroelectric
Right.
phase. So I wonder whether we could use this as an energy-making device.
Have to calculate, but well, in principle, yes. I guess it just depends on how big the effect would be. Right.
Okay, then I'll go on with another question if nobody else. So, all this that is really wonderful right now. How? Let me make the two levels of questions. So, first of all, in general, how a mathematician can contribute to advance this, and then the second question that would be related. So, you talked about polarizations and solving for the electric field, but there is no, or at least in this perspective, you haven't talked about what this does to, say, the alignment of the liquid crystal. So what I mean is, if we take a problem, say, lasing, or a problem like that, so how important could be to study the full description of the director, or even is there any flow that goes on? Because there must be some kind of flow. Would this be important to be studied? Or is just some accessorial thing that one can do without? Right? And if flow is important, you talk about, for example, this that you have these kinds of torques that say the electric field is going to, acting on the, so there's a torque that acts on the pneumatic molecule. So, and then could you possibly conceive a problem where this effect could be comparable to, say, the inertia that we have in Leslie Erickson? The rotational inertia, we always drop. Is there any problem where you would think that, okay, let's keep rotational inertia because there's very serious torques going on anyhow? I don't know if it makes sense.
Okay, so certainly I didn't indicate a really bad job of indicating the role of mathematics, but I think that there's a tremendous amount of possibility all over the place that I didn't say clearly. One is just in this issue of free volume of particles. I mean, the statistical mechanics, I think, really needs more work, but the problem is really challenging. Like, even hard spheres don't have an equation of state. We need an equation of state for liquid crystals, and I think that's an area where sort of geometry plays an important role, and there I think big contributions can be made. And I think to study experimentally the equation of state, to see what the effects of pressure are on these systems, we simply don't know. Very few experiments have been done with inconclusive results. So I think that understanding the statistical physics of liquid crystals is really key. And transport, of course, is even more complicated, but there are certainly scenarios where light-induced momentum transfer gives rise to continuous rotation, like in other molecular motor scenarios. So that I think is there.
So you think that maybe we don't have enough experiments to be able to study the effect of flow when all this goes on?
Well, that may be part of the problem. Yeah, relatively few people are studying that. But now an emerging area I think is, again, liquid crystal elastomers are being looked at again, and they're sort of looking at viscoelasticity, light-induced effects. I think there's a lot of possibility there. And there's a lot of really challenging math in the description of those systems. So I think that that's a really promising area.
Okay, any other questions? If not, that's the one for the day. Thank you.